further ado, Neil.
Okay, thanks, Mike. I'm going to talk about some work that I did with Josh Dunfield on doing bidirectional type inference for a type system with a large collection of type system features. And the title is a mouthful, but what it's really about is about the hot new type system feature of POPL 2003, GADTs, or Generalized Algebraic Data Types. And so the idea behind generalized algebraic data types is that often you want to index, often you want types to reflect more information than just structural things like I have a list with some element type. You may want to track additional information like the length of the list. So this is the hello world of GADTs, length indexed vectors. And so we have this data type definition, vec, which is basically a linked list that carries some additional information at compile time about its length. And so we know that the nil case is a list of length 0, and so the type of nil is vector 0a. So it's the type of a length 0 lists. And the way that cons works is that if you have a head element and a tail of length n, then the resulting vector will have length successor n. So consing something onto a list adds 1 to its length. And so now this vector type is tracking some additional information, and we can use it for hopefully productive purposes. So for instance, one of the first things that we teach students to write in an introductory programming language class is something like the head function. So if you have a list, you want to produce the first element, and you say, okay, if I have a list of element type A, I'll produce an A. And the way I'll do this is, if it's a cons, then I'll just return the first element. So cons xx's will return x. And in Haskell 98 or standard ML, what will happen is that this function is a partial function. But with GADTs, this goes from being a partial function to being a total function. So this is a complete set of patterns because we know that the type of the argument is vector successor of n. And since 0 is not equal to successor of anything, we know we don't need the nil pattern. And furthermore, we can carry along these properties as we write functions. So the map function is something which takes a function from A to B and will take a vector of length n containing A's into a vector of length n producing B's. And the definition just says apply f to each of the elements pointwise. And so the additional information we have in this definition is that a map is a length-preserving function. If you give it an n-element input, it'll produce an n-element output. And that's not always the case. So now the type filter, what it does is it's given a predicate, a arrow bool, and a vector. And instead of returning something of length n, it says there exists some k such that I return a vector of length k, because we don't know whether any given element of this list will satisfy the predicate or not. And so now the types of these two functions distinguish whether the function is length preserving or not. And so it's actually quite a lot of fun to program with these things. Like the first few hours, you struggle with these type errors, and then you're like really happy about when a program type checks. And so the question is, like, why doesn't every functional programming support it? And the answer is that implementing GADTs is actually pretty tricky. You need quite a bit of specialized expertise to do it well. And in fact, it's sort of to the point where if you do have this expertise, you're probably on a first name basis with one of these people. So hi, Stephanie. Hi, Frank. I understand Frank had to leave all of a sudden, and I don't know if Jacques is here or not. But these are all nice people, and they're totally willing to help people implement advanced type systems. But there are more type systems to implement than these people have hours in the day. And so that leads to the research question of this paper, which is, can we present a type system for implementing GADTs that fits into one paper? And putting a core calculus into a paper is pretty easy, but when you want a type system that corresponds to something people can actually program with, it's actually a lot of work. And because this is type systems work, the methodological approach is, as always, to turn to the Curry-Howard correspondence. So we'll turn to the Curry-Howard correspondence, decompose GADTs into their logical primitives, and then hit this logic with modern proof theory. And then the result will be a type system suitable for algorithmic implementation. And In this talk, what I'll talk about are just two of the type system features, two of the logical features that end up being turned into components of our type system. So we'll talk about how we propagate equality types through the system and how we support existential quantification. So equality types. So the usual folklore story about GADTs is that they correspond to first-order logic. So we have simple types corresponding to propositional logic, and if you want to talk about fancier properties, you might move to logic like first-order logic. So you can think of vector as a predicate, and the indexes in these data types correspond to arguments to predicates. And the surprising thing is that the proof theory of first-order logic with equality is something that was only sorted out very recently. So if you look for the sequent calculus rules for first-order logic with equality, you'll discover that the well-behaved rules for them were only discovered in the 1990s by the logicians Jean-Yves Girard and Peter Schroeder-Heister. And before that, you could add them equality axiomatically to a system, but rules that satisfied logical properties like cut elimination weren't known until their work. And so the way they introduced equality into the sequent calculus, part of it looks very familiar. So the introduction rule for equality is just the reflexivity axiom. So we can always assert that T is equal to T. And if you're used to Martin-Wolf type theory and its identity type, this looks very familiar because reflexivity is the constructor for the identity type. But the elimination rule that Girard and Schroeder-Heister found is very unusual. And just taking one look at it will tell you why no one discovered it for a half century after the discovery of the sequent calculus. So what this says is if we have S equals T as an assumption, the way that we use this assumption is by finding a complete set of unifiers for these two terms. So we say S and T are terms in some algebraic theory, and what are all the possible ways that they could be made equal? And so if you have all these possible ways of equating these two terms, we can propagate this equality information into our proof by applying these substitutions to both all the assumptions and the goals. And so if we can find a proof for every possible way that these two terms can be made equal, then we've sort of successfully used this equality proof to derive the conclusion. And this kind of quantification plus implication structure in the rule is quite unusual in sequent calculus presentations. And so it's sort of helpful to look at a couple of examples of its use. So there's the left rule for equality elimination. And so let's look at a concrete instance. So first, suppose that our assumption is 2 equals 2. And so in this case, the equality is a really basic tautology. So 2 equals 2 is sort of the same thing as true. And we're not actually going to make any progress in our proof from it. And conveniently, the most general unifier of 2 and 2 is the identity substitution. So the Schroeder-Heister rule says, well, if you have this tautological fact, it just goes away when you eliminate it. And sort of at the other extreme, suppose we had an impossible case, like 1 equals 0. So now what we've done is we've assumed something false. And the Schroeder-Heister rule will say, well, what's a complete set of unifiers for 0 and 1? That's the empty set. There are no unifiers for these terms. And as a result, because it's an implication there, for every substitution in the complete set of unifiers, we have no premises in the specific case of this rule. So we're saying if you make a false assumption, you're done with the proof because ex falso quodlibet. So we have no premises, and this is sort of nice from a proof-theoretic point of view, but it's also nice from a programming point of view. So remember this head function. In the head function, we left out the nil case. And now over on the right, I wrote vector in a slightly more type-theoretic style, where I made all the equalities explicit. So if we have a vector of length n, the nil case says, well, if the vector is length n and you have a nil, n has to be equal to 0. And for the cons case, we say, well, if we have a vector of length n and it's produced by a cons, well, there has to be some k such that successor of k is equal to n. The tail has to be one shorter than n. And the head is an a, and the tail is a vector of length k. And so in this particular case, when the length of the vector is successor of j, we can substitute that in for n, and we can see what happens. And so now in the nil case, what we've got is we say we can construct, we can use nil to construct a vector of length successor j if we have a proof that successor of j is equal to 0. And that's a false assumption, and the Schroeder-Heister rule says, well, you don't need to do anything for this, because this is impossible. And that corresponds exactly to the feature of GADT coverage checking, that you can omit the impossible cases. Okay, so next, let's look at another feature of the logical interpretation of GADTs. So what we saw is that once we made our equalities explicit, we needed some existential types. So in the cons case, we needed to say if we have a vector of length n, then the tail has to be something that's a bit shorter. So we say we have to have a number such that the successor of k is equal to n, and the tail is length k. And so we've introduced an existential type into this type declaration. And now, if you've worked on type inference, you should be feeling a little bit alarmed. And if you are thinking of this from a logical perspective, you shouldn't be alarmed at all. Like, it's a perfectly ordinary logical connective. We can use it to do all sorts of things, like, say, a list is a vector of length k for some k. It all makes sense logically. But from a programming point of, from a programming language implementation point of view, it's a little bit worrisome. And the reason is that in order to write programs, we need universal quantification. And for functions like filter, we have both for all and exist appearing in the type. And this has historically caused a lot of problems with type inference. And to understand why, let's see how type inference can be formulated in a sort of logical style. So suppose we have these three functions, map, toString, and x's. So map has the type on we expect on vectors, where it takes vectors of length n and element type A to vectors of length n and element type B. ToString takes integers to strings, and x's is just some list, which is a list of integers of length 7. And so if we write map toString x's, we expect a result of the form, we expect the result to have the type vector7 string. So we've mapped toString over all of these elements, and the length is the same. And what we absolutely don't want to write is something like this, map int string7 toString x's, where we instantiate all of these quantifiers explicitly. So the point is we want to omit the explicit type applications here. And we just want to use map at this instantiated type. We want to say map has this polymorphic type, and it also has this more concrete type, int arrow string to vector7 int to vector7 string. And this kind of thing can be modeled by subtyping. And so the idea is that we can model this sort of instantiation by a subtyping order, where we say a polymorphic type is a subtype of its instantiation. And when we put in these subtyping rules, you can see in the for all left rule that you have to guess the instantiation. And if you can guess this instantiation, then you're doing well. And in practice, we do this using some kind of unification algorithm. And it's also the case that exactly the dual rules work for existential types. So now when you have existential types, when it's on the left, we say we have to prove the subtype entailment uniformly. And when the existential is on the right, we have to guess the instantiation. And again, if we just had existential types, we could use unification and solve things. But when we have both, logically everything is perfectly sensible, but implementing it is tricky. And the tricky issue is that when you have subtype entailments of the form for all alpha A is a subtype of exists beta.b, now you have some choices about how to proceed. You can either guess the existential first and then guess the universal, or you can guess the universal first and then the existential. And you can't predict which one you want by just looking at the outermost constructors. And you can construct examples where you need to do one first or the other. And so in an implementation, you end up needing to add some backtracking. And this is like very bad from a predictability and performance standpoint. So what we wanted to do is we wanted to say, let's select an order so that this kind of backtracking search doesn't occur. And just picking an order wouldn't work because maybe it would lead to some bad guesses. But we realized we could adopt an idea from polarized type theory. And in polarized type theory, types are divided into two classes: the value types, which are things like integers and booleans and sums and strict products, and the computation types, which are things like functions or lazy pairs. And what you can do is you can say, well, if you have two classes of types, you've got two different subtyping relations. And oh, by a remarkable coincidence, existentials behave more like values because you just package together a value and hide the representation type. And universals are like big lambdas, so they behave a bit like functions. And because these two for alls and exists are in two different subtype relations, the whole issue of how to choose which one to instantiate simply doesn't arise. And furthermore, because focalization is so proof-theoretically well behaved, like it almost never picks you never run into a case where you expect some subtype relation to hold that doesn't. Joshua and I tried, and we couldn't find any examples where it didn't do what we wanted. And so to make it, to give a polarized subtype relation, we just take the original one, and then we just introduce two subtype relations, one for the negatives, one for the positives, and then we add some rules to shift between these two when you're forced to. And now we have a syntax-directed subtyping relation again, and we've got universals and existentials coexisting in the same type system. So that was a really nice payoff here. And so there's actually a lot more in this paper. So in order to actually get a full type system, we needed to look at a lot of other things. So in languages like OCaml and Haskell, all of the equality proofs are passed around implicitly. And to model this, we moved from French proof theory to Italian proof theory, and we started using some intersection types. And we also needed to come up with like some new ideas, like getting the type system to track explicitly whether it was producing a principal type or not. And the polarization also led to like a clean account of things like pattern matching. And so we were able to give an algorithmic system to go along with the declarative system and also prove that everything is sound and complete. So there's our pattern matching judgment. You can actually read it in the paper rather than just seeing it here. And so, this might lead to a question. Okay, there's a lot of rules there. Does this actually work? Is it too hard for anyone to implement? And to answer this question, I want to show you this person. His name is Soham Chowdhury. I've never met him. I've never even talked to him. I believe Joshua has tweeted at him and maybe answered one email that he sent us, or maybe two emails, I don't know, when Soham read a draft of our paper and then went ahead and implemented most of it. And since he's just an undergraduate, I think it's at least empirical evidence that people who aren't us can read our paper and implement this type system. So in conclusion, I just want to say
That's existential, not a universal.
it's a yes. So yes. So in conclusion, by taking Curry Howard a bit more seriously than usual and using a bit more proof theory than usual, we have like a feasible and implementable algorithm with I think a very nice specification. Thank you.
So if you have a question, someone will walk around with a microphone. I'm going to ask a question that came through on Slido first, but if you have a question, please raise your hand and we'll come to you. The question is, I have to pick one. Do you have any examples where the CSU contains more than one substitution? You didn't show them in the talk, and is this reflected in any way in the surface syntax?
So that's a very good question. So in our type system, we just used index terms like you have in in CAML and Haskell. And if you have a term, two terms without like any equations on them, then the regular unification algorithm applies, and there's at most one most general unifier. So our approach would work without any backtracking if you pick any other algorithm with most general unifiers, like abelian groups or things like that. But if you pick something else, like I think there are theories where you have large but finite sets of potential unifiers, and in that case, you actually would have to do backtracking. But in the paper, we picked the kind of thing that shows up in CAML and Haskell, where there are most general unifiers.
Okay, I have another one from Slido then. Can the technique be extended beyond GADTs to support full dependent types?
That's another good question, and the answer is we believe that's future work. So the main issue is that in a full dependent type system, there's the reductions occur alongside as part of the conversion judgment. And if you introduce unification variables, there's all sorts of questions about, what happens if these unification variables are duplicated or go away when beta reductions happen. And finding things that keep you from having to do full higher order unification, which is undecidable, is something we don't know how to do yet, and that's why it's future work.
I don't know whether to stand up or sit down. So you split strict and lazy products into your two separate, values and computation. But so I think of them from a dependently typed view as specific, like a specialization of sigma types. Would they not get split between the two categories as well?
Secretly what's going on here is something like call by push value is occurring, where you distinguish between values and computations. And integrating call by push value with sort of dependent type theory is still sort of an open question, because there's first the question of how do effects interact with dependent types, and secondly there's the question of like how can you be dependent upon a computation, and we don't know the answers to those questions, so I just can't guess how it would interact with type inference.
Thank you.
Okay, there's a couple more questions on Slido which you should look at,
okay.
and let's thank the speaker.